Hello, everyone. My name is Arindam, and this is my presentation for my master's project, which is to create a Python SDK for Next.Res. I would also like to take this opportunity to thank Professor Sudoki, who has been my mentor and guided me throughout my time here at UC Davis. Okay, so I'll quickly go over the table of contents where first I go through the motivation and the objective, then project contributions, then a few core concepts, finally a short demo and architecture and transaction flow, and I'll end with challenges and future work related to this project. Okay, so what was the motivation behind creating this SDK? Initially, we started with the objective of making a marketplace on top of ResilientDB, NFT marketplace, which is non-fungible tokens. And while we tried to do that, we felt that there were certain things which was needed in ResilientDB before a marketplace could be created on top of it. So first, let's understand what is ResilientDB or Next.Res. Next.Res is basically the next generation of ResilientDB. It is a high throughput yielding permission blockchain fabric. And it's essentially a consensus engine which supports different consensus protocols like PBFT. It also has a key value store with a durable storage. And it's completely written in C++. So all the APIs or the endpoints that it had to communicate with the database was via C++. Now, the issues that we faced while building on top of ResilientDB as it was is that there was no easy way to create or transfer assets. So while creating something like a NFT marketplace, which is basically a token, so we would want to create and transfer assets, right? And when you're creating and transferring assets, it is not as simple as just putting something as a key value pair. We need stuff like validation of transactions. Ownership is a very important thing. There has to be proper signatures, and a transaction cannot be duplicated or it cannot be double spent. Means if there's if a person has only 2 tokens, let's say the person shouldn't be able to spend more than 2 tokens. So we had to take care of all those stuff. And also ResilientDB was written in C++, and we wanted it to have modern backend language support like Python, so that a backend framework like Django or Fast API could be used to create NFT marketplaces. Okay, so I'll go over my project contribution, and it can basically be summed up as trying to create a UTXO model on Next.Res. So I'll go over what UTXO is shortly. It basically means unspent transaction output. So to make the UTXO model, firstly, I have to create a Python SDK which prepares the transaction, signs and fulfills the transaction, and sends the transaction over REST endpoints. And then I had to create a interface on the KV client or the key value client, which now exports some REST endpoints written in C++, and it has basic functionality of to post a transaction and to get a transaction, and also the transaction validation, which validates the signatures, double spend, duplicate transaction, and other stuff among this. So the SDK and the KB interfaces on the client side of things, and the validation happens on the federated nodes of Next.Res. All right, so let's go over some core concepts related to my contributions. First of all, what are transactions? So it basically enforces a UTXO model. Now, what exactly is a UTXO? So unspent transaction output refers to the output that can be used as an input to a new transaction, right? In a sense, a UTXO defines where each blockchain transaction starts and finishes. The UTXO model is a fundamental element in uh, 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 cryptocurrencies like Bitcoin and other coins. So it can sort of be thought of in term as a dollar bill, wherein when you spend a dollar, you get certain changes back, right? But that dollar bill is spent. Okay, so this transactions that I'm talking about, it encodes information such as public keys, which are uh, of the owners of the asset, and then fulfillment of previous transaction. By fulfillment, I mean this is what is used to verify if the right owners have actually signed this transaction. And then it also has asset information. So uh, asset can be anything which is tangible or non-tangible. And finally, this transaction model has been inspired from BigchainDB's transaction spec. Okay, so I'll go over the transaction structure as well. First of all is the asset. So it is a digital or physical item that cannot be changed once registered. So something like if you have a cycle, maybe you can uh, have unchangeable parts of the cycle, like the serial number of the cycle registered as part of the asset, right? Then comes the metadata. This is the mutable part of a transaction. So a metadata can be updated, which can be things like prices, age, like let's say age of the cycle or the price of the cycle. Then we have the inputs. So inputs can be thought of as the to unlock a previous transaction. This is what contains the proof that yes, this transaction is indeed valid, because it has the correct signatures and it points to the correct previous transaction. So, and we have also the output field, which contains the condition that needs to be fulfilled for a transfer transaction. So whenever we create a transaction, you want to transfer it, there has to be certain conditions that has to be fulfilled. For example, the condition is if I'm the owner of this asset, you need my signature to transfer it. That is a condition, right? So that is encoded inside the output field. And finally, the operation, which we support only two operations right now, which is to create and to transfer. So while creating, there is no fulfillment inside inputs. That means there's no proof that this has been signed correctly by a previous owner, because there is no previous owner. But for transfer transaction, the inputs become extremely important for verification. And finally, we have the ID field, which is a SHA-256 hash of this entire transaction after it's fulfilled. So to give a demonstration of how the UTXO model works, let's say we have this first transaction, which is a create transaction. And it, as I mentioned, because it's a create transaction, doesn't fulfill anything, but it has two outputs, which is output 1 and output 2. And then we have this another create transaction, which also has output 0 and output 1 for both, sorry, output 0 and output 1. So this transaction has two outputs, and this transaction also has two outputs. Now, when we want to have a transfer transaction, we can create this transaction T3, which is a transfer transaction, and it fulfills two inputs. The first input is from transaction T1 and output 1, and the second input is from transaction T2 and output 0. So it fulfills this particular outputs, and then it makes a condition for its future transfer in the output section. Now, once this two conditions or two outputs have been fulfilled, it's considered spent. That means this two outputs cannot be spent elsewhere. So and this outputs, it's very abstracted. It can have a lot of information like how much quantity of an asset is there and stuff like that. So, but once it has been fulfilled by any other transaction, this cannot be used anywhere else. This particular and a specific output is like uniquely represented by the transaction ID and its output index. Okay, let's see how the transaction is validated. So once the transaction reaches the federated nodes of NextRes, the inputs fields of the transaction is what is essentially validated, which has the proofs of the signatures of the right owner. So we use ED25519 public key signature or cryptography to validate if the output of a transaction is fulfilled by the correct owner. What this means is we first, in the inputs, it's encoded which transaction it validates. So we first fetch those previous transactions, and then we also have access to the private keys. So we can prepare the transactions locally in the verification stage with the public key, sorry, not the private key. We have access to the public key. We locally create the transaction, and inside the inputs field, there is the fulfillment or the proof that it has been actually signed by the right owner's private key, right? So we have all the three ingredients that's required. We build the message, we have the public key, and we have the signed message with the owner's private key. So that's how we can use this implementation of this cryptography to verify if the signatures match with the message. Okay, and in validation, we prevent double spend by checking if the transaction ID and the index of the output is part of any input of existing or queued transaction. Like it's possible that a transaction exists in the queue which has not been committed yet. The consensus is still going on, or if it can be like a duplicate transaction. A user might have added two transactions in a short span of time, which is basically the exact same transaction, and only if it's not double spent, then the transaction goes through. These are few of the validation that happens. There are way more validations, like the structure validation, and there's more detail about it in the blog. Okay, so I will quickly demonstrate. Okay, yeah, I'll quickly demonstrate the application and how creation and transfer of asset works. So here I have a 4-node network running of NextRes, and I have the client also up and running on this port 1800. So to create, okay, so this is how the entire SDK works. To establish a connection, it's as easy as calling ResDB and passing the URL, and that's it. That establishes the connection to the database. And then what we do over here is also create two users, Alice and Bob. So Alice, we have Alice's private key and public key created. So a user is identified with their public key and private key. All right, now let's create an asset. So we are here creating a, this is a token. Let's call it PS5 instead of Game Boy because it's for PS5. So we have a PS5 token, which has data and it has fields like token for and description. So the only important field is the data. It can have uh, any other fields as well, but data is important to have. All the details about how an asset should be is also presented in the blog. So once the asset is created, what we need to do is uh, prepare the transaction with the digital asset. So preparing means we make the JSON structure and we give it the correct public keys. So over here, when we're preparing the transaction, we just call on the prepare method and we give the operation as create. The signers is Alice's public key, and the recipient is um, Bob's public key. So Bob is the recipient, and instead of 10, let's just make it into a single token, and the asset is the PS5 token. So once we do this, oops, let me run this again. Okay, so now the transaction is prepared. Now, although it's prepared, it's not fulfilled. That means it's not signed by with the private key of the owner. So we want to sign it with private key of Alice, who is the owner. So we just call on the fulfill method and we pass the prepared transaction, and then we give the private key of the owner, who is Alice. So if you run this, now the transaction is fulfilled. So if I show this transaction, this is how it looks. So we have the inputs field, which has owners before. In this case, it's the current owner because it's the create transaction. And as I mentioned, it does not fulfill anything. Input is basically the key which unlocks previous transactions, proof of that. It has this fulfillment, which is the signature with the private key of the owner. And then it has the output, the condition as to who can whose signature is required in order to transfer this asset or this token, right? And in this case, over here you have few things such as the condition details, like it is using 25519 with SHA-256 for hashing, and this is the public key of and then it also has this URI, which is part of something called crypto conditions, which is used for easily encoding and decoding information into a URL. So this part of the URL has information of the owners whose private key is required, and the transactions and other stuff. Basically, an easy way to encode decode information. And we have the amount as one, the operation as create. There is no metadata. We haven't added any metadata over here. And finally, the asset. And we also have the ID, which is the hash of the transaction. Okay, so once the transaction has been fulfilled, we run the cell to commit the transaction. And when we use this method to send commit, it basically sends this transaction to the to NextRes, which commits it. Over here, you can see it has received the transaction and it has committed the transaction. That's why we get this in return, the ID of the transaction. So now that we have the ID, we can use this ID to fetch this current transaction as well. from next res. Instead of this, you can just pass in the ID. And if I run this, I get the same transaction back again. And over here also, we can see that this is the endpoint that has been accessed, and we got the transaction back. All right. So once this is just to create a simple transaction, but let's see what happens when we have to transfer it. So while transferring the transaction, again, first we have to prepare the transaction. So so when we are transferring the transaction, we don't really have to keep all the details of the asset inside the asset field, because as I mentioned, asset is a stationary thing. It's a static thing. It does not change. So we can just give the ID of the create asset in the create transaction. Then we have the output index, which is basically the output index of the transaction this fulfills. And we get, and we have other stuff like fulfillment, which is the details of the conditions that it fulfills. And we have this fulfill field, which has the output index and the transaction ID. As I mentioned, transaction ID and the index uniquely identifies token, or output of a transaction. Also, it has the owners before field. So if we run this, then we have this transfer input dictionary made. And then finally, to prepare the transaction, we have, we can call on the prepare method again, but in this case, we are transferring the transaction. So the operation is transfer, and the asset is transferred asset, which basically just has the ID, and the inputs is the transfer inputs, which has all the conditions as to which exact output it refers to, right? And it has, and we can specify the recipients. In this case, I want, since we have just one token, so there should be just one. So we are again we are making Alice the recipient with just one token again. So let's run this. Okay, so now the transaction is prepared, and now we'll fulfill this transaction using Bob's private key, because Bob was the previous owner of the transaction, and now we're trying to change the owner from Bob to Alice. So let's run this. Okay, and this goes through as well. So if we check the fulfill transaction, we get this JSON output. This has the inputs field again, which has the owners before, and it shows Bob as the owner before. And then there's the transaction ID, which it fulfills. This is the transaction, and the transaction index, which it fulfills. This one uniquely identified output of transaction. And this has the fulfillment, which has all the which has the message digest, which has been signed by the private key of the previous owner. And then finally, finally the output has the public key of Alice, because now the new owner is Alice. And then it has also the same details as the create condition, which is a create transaction, which is the condition to unlock this particular transaction, which is same thing again, ED 25519, the public keys, the URI, the amount, operation. There's no metadata again. The asset over here is not the complete asset, but just the ID. And finally, the new ID of this transaction. And then again, this transaction can be committed and sent to ResilientDB. Okay, so let's get back to the presentation. Oops. All right. So now that we saw how to use the SDK, let's see what's happening a little bit in the backend and how the flow is. First of all, the architecture of ResilientDB or NextRes. First layer is the SDK, where I just demonstrated the Python SDK, and it connects with the interface or the KB interface in this particular case over REST APIs, and then it interacts with the entire service using TCP sockets over the networking driver or networking module that exists. So once it reaches the service, there are it has first is the platform, which has different consensus managers, which has the consensus manager to manage different consensus protocols like PBFT, GOBFT, and then it goes to the transaction manager. This is where the validation happens for my particular UTXO model, and then finally it goes to the chain where it is stored in chain and also in durability layer, where we support levels DB and rocks DB. So how does the transaction flow? So first we prepare the transaction, and then we fulfill the transaction, which is signing the transaction, and then there is a verification of this transaction, which happens in the server side, and finally the commitment. Right. So if we see this in a time graph or time flow of events, over here we can, first thing is the Python client, which prepares and signs the transaction, and then it sends a transaction to the KV or key value client, which is also in C++, and then it goes to the federated nodes of ResDB, and then once it reaches the transaction manager, there is a Python binding which for the validation. So the validator is written in Python, and it is called via a binding, and then it validates all the inputs. So we get all these previous transactions and its particular output indexes from the durability layer, which is part of the storage. So it's a backend. We do that back and forth till we get all the transactions. Finally, after transaction is validated on all the aspects, it returns it back to the transaction manager, and then it serializes and sends the transaction to the consensus engine. And then once the consensus is done, it executes and commits the transaction. Right. And then finally, we get the success or failure message in the client. Okay, so few challenges. First is to securely store private keys. So as I show that it's easy to make private and public keys of a user, but we need to figure out a way to securely store the private keys, or else it might be difficult to create a big application like marketplace. Okay. Second is the validation is done with the Python binding, and Python sort of makes it slow. So we need to do it in C++, but C++ does not have some libraries which is well maintained that we need. For example, it's the crypto conditions library. So currently we are working on validating in C++. We have a library that we have to that we need to modify ourselves in order to make crypto conditions work. And then we also need a persistent storage which allows for complex queries. So the persistent storage, as I mentioned, was levelsDB and rocksDB, but they do not allow for complex query within the JSON structure. So we need to expand to storage which allows that. That will give the SDK a more rich set of functionalities. also for creating an asset, we just need signature from any random owner there's no verification as to if the receipt, I can create a transaction and I can assign it to someone else currently, but ideally the signature of both the parties should be involved in order to even create a transaction. So that's part of a future work as well. And finally, to have more ways of exploring the ResilientDB network from the SDK, like block size, and the number of transactions that's happening, and all sort of metadata, which can be also added as different methods in the SDK. And then the SDK is not packaged to PyPy right now, but I believe by packaging it to PyPy, it'll make it more easy to download and dive right into using the SDK. Okay, so that's about it. Thank you for listening.